Okay, so the derivation for if you want to find the derivative, if you have a function,
Mhm.
sorry, let me adjust this. So if you have a function, still
Mhm.
too thick, hold on. Okay, if you have a function f of x, right? And we
Mhm.
say g of x is equal to the inverse of f of x,
Yeah.
right?
Uh-huh.
Then if you plug in f of x into each of these values, this equation should still hold, right? So we plug in
Exactly.
f of
It
x
should
for
be
x.
equal.
Yeah, so g of f of x equals just x, right? Now if you
Yes.
take the derivative of both sides, you'll get from here the chain rule, right? If we take the
Uh-huh.
derivative with respect to x on both sides. So if let's say the problem is because let's say it's like f inverse of 2, right? Well, that's the same as g of 2, right?
Yes.
Or
Ah.
the derivative of the inverse at 2 is equal to g prime of 2, right? Does that make
Oh,
sense
wait, hold
so
on.
far?
So G,
Like
if
if it was like y equals x squared, obviously this is easy to take the inverse of. But let's say it asks for the derivative of the inverse at x equals 2 or something like that, right? Because we
Mhm.
said g of x is equal to f inverse of x, all I'm saying is that's equal to g prime of 2, right? Does that make sense? Just that. If not, I can try re-explaining it.
Wait, hold on. I just need to look at the diagram a bit more. Give me like 15 seconds. So f of x, so g of x equals inverse of f of x. So if you plug in f
So
of x equals x, and you take
yeah,
chain rule. But then for this one, it's that f of inverse 2 needs to be equal to g, derivative of g over 2.
the derivative of the inverse at x equals 2. This is f inverse prime of 2 equals g prime of 2. The derivation isn't done yet. We're not done here yet. I just wanted to make
Yeah.
sure that was clear.
Right.
Is that part clear?
Yeah. So the
Okay.
derivative of the inverse at x equals 2 is equals to. Yeah, sorry, I kind of flipped it around. So yeah, I get what
Right
you're saying.
there?
Yeah.
Okay. So if I'm looking for g prime of 2, then I have to find what I can get for f of x such that this becomes g prime of 2, right?
Yeah.
So if let's say here, right, um, the in our original function, if we plug in x equals 2, we get y equals 4, right?
Yeah.
So in our inverse, in g of x, it's going to be g of 4 equals 2, right?
Yeah. Because it's the other way around.
Yeah. So so that means in our inverse, our coordinates is 2, 4. And obviously there's plus or minus. There's actually, right, there's negative 2 comma 4. So then here there's,
Negative 2 comma 4.
or
Yeah.
sorry, wait,
Oh, wait,
this
it's
is,
4 2, right? It should
yeah,
be.
yeah, for the inverse. So the inverse is 4. The inverse points are 4, 2
Then you
or
have negative 4 2.
4, negative 2. Because remember,
Yeah.
it's the negative
Inverse.
on the 2.
Yeah, and it needs to be the same, kind of.
Yeah, so if this is our original here,
Mm-hmm.
right? Those are our original points. And then
Mm-hmm.
here, these are our inverse points, right? We want to
Mm-hmm.
find, and let's just ignore the second one for now and just look at the first one. We want to find, we want to find something that will make g prime of 2. So f of what equals 2, right? Over here, f of, so what will make y 2 here? It'll be root 2, right? So
Yeah,
in our original function, if we plug in root 2, we'll get 2, right?
exactly.
So in our inverse, that point becomes, and obviously there's more with the pluses and minuses, but just ignore that for a second. With our inverse, that becomes this point, right?
Mm-hmm.
So f of, so this, if we want to have g prime of root 2, that's equal to g prime of f of, um, what is it? F of root 2, right?
Mm-hmm.
So that's equal to 1 over, so our x isn't actually 2. Even though it's asking for g prime of 2, our x is not 2, it's root 2. So that's equal to 1 over f prime of root 2. So if we use this equation, that's dy dx equals 2x. If we plug in root 2, that's 2 root 2. So the derivative g prime of 2 is equal to 1 over 2 root 2.
And g prime of 2 is also equals to the inverse of f of x at 2.
Yeah, well g prime of x is equal to the derivative of the inverse at x.
Okay.
Because g of x equals f inverse x. Does that make sense so far, or do you want me to re-explain that? I can explain it easier. Do you have any
Yeah,
questions?
makes sense, but I think I need to do like a couple practice problems of my own. I have like literally like a practice book here. I will do it like
Okay,
sometime.
let me see if
Yeah.
I can explain this a little bit better. Because if I have two functions, let's just say like I have ln of x, which looks like this, right?
Uh-huh. Yes.
Or whoops. And let me draw that in orange because that's our original function. So if you have y equals ln of x, sorry, we're going over the derivative of the inverse. I'll go back to the original derivation in a second. Let me continue this. Right? Our inverse for this function is going to be e to the x, right?
Yeah.
And geometrically, that means that it's reflected across the
Well, so
y
it's going
equals
to be like
x.
y equals x.
Okay, right? So let's say I have a point, let's just say e comma 1, right?
Mm-hmm.
So if I put in e 1, right?
Yeah.
The
So when you plug in
derivative,
e, you get 1.
yeah, for this original function, if you plug in e, you get 1. So the derivative at that point, the slope is going to look like that, right?
Yep.
Okay. But on our inverse, that point is instead 1 comma e, right?
Yeah.
So at 1 comma e, our slope looks like this, right?
Yeah.
Sorry, that was a bad. Our slope looks like that, right?
Mm-hmm.
I should have drawn this more extremely, but if this slope is flipped because it reflects off of y equals x, this slope is growing at 1 over the rate of this slope. If let's say this slope was 2, hold on. Let me see if I can explain this as best I can. If let's say this slope was 2, right?
Mm-hmm.
It's not, but just
Yeah, but just for the sake of
pretend it
brevity.
was 2.
So if it's
So
m
if
equals
it was
2,
2 1, right?
yeah,
Then
then
if
the
we
inverse
if
needs
we
to be 1
then
over.
yeah, the inverse is 1 over 2 because it reflects off of y equals x. Our inverse slope is going to be 1 2. Or that's
Yeah.
stupid as hell. I meant let's just say m equals 1 half over here, right?
Uh-huh.
Then on our inverse slope, it's going to become 1 2, right? And that's 1 over 1 half. So that's 1 over f prime of e is equal to 2. Do you see how
Oh.
geometrically that flipping works?
Oh, that makes so much more sense. Okay. Okay.
Yeah, so that's why we do that. And then Abhinav, if you want to see the derivation, since you joined late, I'll do it real quick.
Right.
Um,
So
yeah. What's your question?
theoretically, all you need to do is find the slope of the find the slope of the tangent and find the derivative for the original function, then flip it over and then set it to 1 over f prime equals e, right?
Yeah, I mean, you have to be careful because if in this question, it would be asking what is g prime or what is f inverse. Don't I don't remember how you draw prime. I'm just gonna do this. F inverse prime of it's going to ask for f inverse prime of 1, right?
Mhm.
But that's not equal to 1 over f prime of 1. That's equal to 1 over f prime of e, because because in our derivation, if you remember, in fact, I'll just do that again real quick off to the side. If g of x equals f inverse of x, then g of f of x is equal to x. So g prime of f of x times f prime of x equals 1. So g prime of f of x equals 1 over f of x. So when it asks for f inverse, if you want me to remove the g, how it would look like is f inverse prime of f of x. Let me do this. F of x is equal to 1 over f prime of x, right? So if it asks for f inverse prime of 1, that's not equal to 1 over f prime of 1, because these are not, the
They're not
x that you're
equal.
plugging in here is not 1. That's f of x.
Oh, so you gotta find
You got to
effectively you gotta
find the
find
x in your original function, right? Because it's not going to give you the inverse. It's going to give you this,
yeah.
your original function. In your original function, you have to find the point that outputs 1,
Okay.
right? And here that's e. If you plug in e to the original function, that outputs 1. So that gets you f inverse prime of 1. And you plug in e here.
Oh,
Is that, I can explain that a little bit better if you have, do you have any questions on that?
so you go through the derivation, then
The
effectively
easiest way to remember it is g of f of x equals 1 over f prime of x. It's g of f of x. So if it, or g prime, sorry, g prime of f of x. So if it's asking you, I know the g is confusing, but it makes a lot of sense here. If I ask you like g prime of 1, you need to find what
what one
x
is
is
in the
so that
context of
f
the
of x
original
becomes 1.
function.
Yeah. So
Okay,
you
yeah.
need to find the x here because these x's are the same, but this is not x. This is f of x. Does that make sense?
Yeah.
Okay,
Okay,
so
yeah,
that's
yeah, that
important.
makes so much more sense, right? Thank you.
Yeah, and there's some few things to watch out. Remember with the x squared there was multiple points. That means that and that's because for f of x the inverse is not a function, right?
Yeah,
And
because it's
if you think about it, that means you're going to get multiple derivatives at each point because there's multiple points at every. It doesn't pass the um like if I took the inverse, if this is y equals x squared, then if I flip the x and y, the function would look like this, and that's not a function because it doesn't pass the vertical line test. For every
mhm,
value you plug in, there's 2 that you get, so you're going to get 2 derivatives.
mhm.
But you don't have to worry about that because if they frame it as f inverse, that means that the inverse is actually a function. So they're never going to ask you if y equals x squared, find f inverse prime of 2 because this does not exist for y equals x squared. There is no inverse function.
Because it's not even a function.
Yeah. So you're only going to get, and that's something that Chen might have skipped. I think he like said something about monotonic functions briefly or something like that.
I'm gonna be honest with you.
Monotonic functions.
We haven't done that yet. We haven't
I
done.
haven't even done that
He
yet.
Okay, but it's
he's
very
probably not
simple.
going to do
It's
that.
very, very simple. It's just monotonic functions are functions that always increase or always decrease. Because if that's the case, then obviously they have an inverse. Because if it did increase and decrease, then all of a sudden it doesn't pass your test for a function.
Yeah.
So it'll only ask you these questions with inverses for monotonic functions.
Basically functions that will always have an inverse, so you don't even have to worry about
Yeah.
non-function
Monotonic,
functions.
yeah, monotonic means it's always increasing or decreasing, which means that it has an inverse, which means that uh they can ask you questions like this about that. And
Right.
there's some manipulation you can do. Like in that page with the monotonic functions, it shows a bunch of integrals.
Mhm.
What it's gonna have you do is convert to the inverse and make a new integral using the inverse. That's simpler because the inverse is simpler. And we'll go over that towards the end because I know there's other stuff you guys want to get to that are closer to your actual quiz on Friday. But this I just wanted to cover because it's really simple. And yeah.
All right, got it.
Okay, is there any other questions?
Can you go over the derivation again?
Yeah, so for an inverse function, right? Let's say you have a function f of x, right? And let's say g of x is equal to the inverse of f of x. Okay? G of x is equal to the inverse of f of x. I know I just wrote that, but I'm going to write it again. If I plug in, and the reason I say plug in, because there's a thing with, if I plug in f of x, right, into x, I know that these are still going to be equivalent. If I wrap around f from here, I can't necessarily guarantee that. There's some stuff with that. It needs to be a specific like operator or some bullshit. Sorry, this is recorded. I probably shouldn't swear, but that you can't. I'm saying specifically if you plug in f of x. Does that make sense so far? Not wrapping f of x. So if you plug in f of x, you get g of f of x equals f inverse of f of x, which is x. So far, does that make sense?
Mm-hmm.
Okay. So then if you take the derivative of both sides, you get g prime, the derivative with respect to x, I should say, g prime of f of x times f prime of x, because that's the chain rule, equals 1. So g prime of f of x, and this is the most important part, is equal to 1 over f prime of x. However, if it asks you, okay, I have a function, what's the derivative of the inverse at 2? That is not equal to 1 over f prime of 2. Because 2 is not x, 2 is f of x. So what that means is, in your function, you have to find what x you can plug in such that f of x is 2. And then that's the x you plug in here, not 2. Does that make sense?
Okay.
So like
Mm-hmm.
if it asked for f prime of 2 or f inverse, let me give like a quick example. Say y is equal to 3x, right? And it asks for the f inverse prime of like let's say 1. Okay, so I know that I want in my original function, which I'm gonna make orange. Hold on. In my original function, I want something that will give me 1 because this is f of x over here. Okay, in my inverse function, that's going to be 1. And that's why this is 1. So, and because it's an inverse, these flip here, and these flip here. So you want to find the thing you plug into f of x. And that'll be, sorry, you want to find the thing you plug into f of x. And this is f of whatever. And this is what you actually use for this 1 over f of f prime of x. Does that make sense? And we can do like an actual concrete problem so that it makes full sense. But so far, is there any questions? Okay, cool.
No, not really.
Okay, so I'll use another linear example because here's the thing. I think I already said this, but I'll repeat it again. If they're going to ask you f prime inverse or f inverse prime of something, if they're going to ask you this in the first place, that means the inverse is a function. So it's never going to ask you that for if the original function is like y equals x squared because the inverse is not an actual function. Because if I flip that around, this is not an actual function because for every x there's multiple y's. That's not an actual function. So the fact, even if they were asking you this in the first place, that means the function has an actual inverse function. And what that means is that the function is monotonic, which means it's always increasing or it's always decreasing, but it's never increasing and then decreasing or anything like that, because the moment you have that, you can't have an inverse. But anyways, that's all to say that for my examples, I'm just going to use linear functions because can't really, or I guess I could use y equals e to the x. And let's say I wanted to find the f inverse of, let's just say e, f inverse prime of e. Okay, first thing I do usually is inverse. In my inverse, it's going to be e. So I usually write my second as an inverse, and this is the original function. And that's going to produce something for my inverse. And that something is going to produce an e on my original function. What x here is going to produce an e? Do you guys know? In my original function, what can I plug in for x so that it produces e?
1? What?
1.
Yeah, 1. So then that means that 1 here, it's 1 there. So this is f of x, this is f inverse of x. Okay, so if I want to find f inverse of e, that's equal to 1 over f prime of 1. This is our original function, so we just need to find f prime of 1. dy dx equals e to the x. So dy dx at x equals 1 is equal to e. So it's 1 over e. That's f inverse prime of e. Does that make sense?
Wait.
Because again, it's g, and remember g is the inverse. It's just I wanted to use a different letter. It's g of f of x is equal to 1 over f prime of x, or g prime of f of x. It's g prime of f of x. It's not g prime of x. So this is not the x you're plugging in.
Okay, yeah. That makes sense.
That's f of x over here. So you need to find the actual x.
Okay, that makes sense.
Okay. Okay, so that's all I wanted to say about inverses and monotonic stuff. And then just so you guys know with that page, I'm going to repeat it again. You'll see a bunch of integrals. The reason that you see integrals is because they want you to convert to the inverse, and then you'll get a way easier integral. When you do the integral, you construct a new integral with the inverse instead. So that's why that's there. And that's why it's monotonic. You can only do those with monotonic functions because monotonic functions have actual inverse functions that you can use an integral on. Okay, so that's that. What else do you guys have for your test on Friday? That isn't even on your test on Friday, so we'll cover other stuff.
The
Our test on
quiz on
Tuesday.
our test on Tuesday.
Oh, really?
Our quiz is on Friday.
Yeah.
So you have a quiz on Friday. That's what I meant,
Yeah.
right?
Yeah.
What's covered
Okay.
on the quiz is the by parts trig sub, and then
So inverse trig integrals, right?
Just
So that's like
every just every integration thing.
so like this.
Yeah, we should probably do that.
Yeah.
That's probably fun.
Did you guys cover that in Chen?
Yeah.
Okay,
We
it's just
did,
parts. Yeah, so u dv, u is equal to sine inverse x.
Ah.
I do this off to the side because I can never remember. Sine u equals x. Shoot. Cosine u times du dx equals 1. U x 1 minus x squared. So it's equal to 1 over cosine u. Cosine u is, so it's equal to 1 over root x 1 minus x squared. There we go. Okay. dv is equal to dx. V is equal to x. So then, if we do it by parts, it's equal to x sine inverse x. X sine inverse x minus v du, which is x over, and that's u sub here. Hold on, let me make this smaller. Okay. So that's u sub, u is equal to 1 minus x squared. So du equals negative 2x dx. So you need a negative 2 here. So that means that becomes a 1/2 on the outside. Does that make sense so far? And then that becomes 1 over root u du, which is equal to u to the negative 1/2 du. So it's equal to x sine inverse x plus 1/2 times 2u to the 1/2, and u in this case is 2 times 1 minus x squared to the 1/2, and then plus c. And then we can simplify here, so that's equal to x sine inverse x plus root 1 minus x squared plus c. Okay, so that's sine inverse x. Does that make sense? Did I miss something? Did I do anything wrong? Okay. So if that's the case, you guys are gonna have to remind me, since you guys learned this in class, are any of the other inverse trig integrals actually any harder than this? I don't remember. I haven't done these in a while.
I didn't do. I don't think
You know what?
they shouldn't be though, because it's the same setup, isn't it?
You know what? We have time, so we're just gonna go through every
It'll be
single
so
one.
for real. I did like 2 of them. So
Yeah, we'll go through
I
every
did
single one right now.
just sneak it.
Cosine inverse x dx. Because it always starts with parts, since that's literally the only thing you can do. Except if it's a definite integral, right? And I think you guys actually had a problem before where it was an inverse trig and it was a definite integral. You can do the thing because within the bounds it's monotonic. The function doesn't have to be monotonic everywhere, but within the bounds it was monotonic, so you could have flipped it and then reconstructed the integral this way with definite bounds. Does that make sense? But anyways, these are indefinite integrals. That's what you guys are learning right now. So u equals, let me know if I'm going too fast or if you have any questions. Du
Okay.
equals, so if cosine u equals x, take the derivative, negative sine u times du dx equals 1. So, and then we got to construct our triangle. Cosine u is equal to x, that's x1 square root 1 minus x squared. So this is du dx equals negative 1 over square root 1 minus x squared. If I'm not mistaken, that is correct. So negative 1 over square root 1 minus x squared. dv is equal to dx. V is equal to x. Okay, cool. So you get that the whole thing is equal to uv, so x cosine inverse x minus v du. So that's plus x over square root 1 minus x squared dx. Do I really need to go any further? This is just u sub, and it's like the same thing. Is that good? Are we good there? Okay, cool. So we'll go to the next one. The next one is, I don't know, what is the next one? Do we want to do tangent inverse? Tangent inverse x dx. So u is equal to tangent inverse x. Do this off to the side, which you should always do. If you're memorizing the inverse trig derivatives, you're doing it wrong. Tangent u equals x. So this is x1, and then this over here is 1 plus x squared, square root of 1 plus x squared. We take the derivative here, so it's secant squared u times du dx equals 1. Du dx equals 1 over secant squared u. Secant squared is cosine. Cosine here is that. So it's just 1 over 1 plus x squared. Okay, cool. So du is equal to 1 over 1 plus x squared dx. I think I might have forgotten that in the earlier ones, but it should be there. And then, okay, v equals dx, v equals x. So this whole thing's equal to uv x. And this is always interesting, but it reveals itself pretty obviously with inverse trig functions. You can really tell that parts is just the product rule remixed, because if we write this out minus v du. That's x over. It's very clear that we're just doing a derivative with product rule, and then we're just compensating by subtracting out what we don't like. It's very obvious when you see it as an inverse trig. But anyways, do I need to go any further here? This is also u sub 1 over u du.
I think it makes sense.
Okay, so we'll go to the next one. Next one, cotangent. We'll do cotangent inverse. Sorry, I don't know what I'm doing. This should be u. dv. So u equals cotangent inverse x. Cotangent u equals x. Cotangent, we take the derivative of cotangent, that's negative cosecant squared. First, I should construct the triangle. Let me do that. I should do this off to the side. Okay, so then you take the derivative, you get negative cosecant squared u times du dx. And what are we taking the derivative of? We're taking it with respect to x here. It's always important to know you're not just taking the derivative, you're taking it with respect to something. Okay, cosecant squared here, so sine is 1 over this. Cosecant would just be that. So it's negative 1 plus squared times du dx equals 1. Okay, so du dx equals 1 over negative 1 over 1 plus x squared. Do I need to keep going, or it's pretty obvious this is just going to become the same thing but with the negative flipped in our parts? Does that make sense? Are we good there, or should I keep going? Okay, are you sure? Is everyone good? Yeah.
The like tangent to the fourth, stuff like that.
Yeah, we'll do that after the inverse trig. I just want to go over every single inverse trig first, since we're at it. And then we'll go over trig functions to a certain power. So cotangent, let's do cosecant inverse x dx u dv. So off to the side, cosecant u equals x. Construct our triangle relationship. This is u, x1, 1 minus x squared. This is negative cosecant u cotangent u times 2u equals dx. I should probably just do dx. Okay, equals 1. Cosecant, so that's negative x times cotangent here is, so du dx equals negative 1 over x square root 1 minus x squared. Okay, so du equals negative 1 over x square root 1 minus x squared dx. dv equals dx. v equals x. Okay, we're good there. So that's equal to x cosecant inverse x uv minus v du. Okay, and then we get something interesting here because we can't use u sub. That's equal to 1 over, but we can use trig sub. So we're going to construct another triangle. 1, x. Okay. And, okay, and then that's theta. So secant theta equals 1 over, so that's one of our components, but we need a dx still. Sine theta equals x, cosine theta d theta equals dx. Okay, so we have that. So this is equal to, off to the side, I'm going to do it. Secant theta cosine theta d theta. So that's just d theta. Those cancel out. So it is theta. And the easiest thing here is to use this one. Sine inverse x equals theta. Yeah. And why do we use a capital S here? Because if we wanted to plug in any x, we can get a full range of numbers out of. No, we cannot. If we, yeah, we can plug in any x we want here, and there will be an answer just within our restricted domain. So that's why we can capitalize this safely. Sine inverse x equals theta. So here it's just sine inverse x. Okay, are we good there? Do you guys want me to do we do secant x already? It's going to be the same thing, I suspect. Just flipped. A few things flipped. Okay, are we good? Any questions? I can put this back up. Do we have any questions?
No, not really. I think that's good.
Okay, cool. Okay. Let's see. What's the next thing you guys do? You guys want to do integrals of trig functions to different powers. So remind me again, how far do you guys go up? Do you guys go to the fifth?
He said not more than the fourth, I believe, today.
Okay. We'll just, since we have the time, I'm here until 8. Is there anything else other than that that we haven't covered already?
Wait, did you do the? I stepped away for a second. Did you do the tangent to the fourth or no?
I will do that. I'm gonna do every single trig function up to the first to the fourth power. But before
Okay.
I do that, I want to make sure there's nothing else. Is that the last thing you guys are gonna do in your quiz, or is there anything I haven't covered yet?
I think that's it for the quiz.
Okay,
No,
so then once I do
there's like,
that,
did you do like cinch cosh? I mean, that's pretty intuitive though.
okay, I'll go over that. So sinh x is equal to e to the negative x. Make sure you guys, that's correct, right? I might be wrong.
Yeah.
Is it plus here?
Should be, right?
I don't know. Do you guys
Pretty
have
sure
that in your
sine
notes?
is minus.
Okay, cool, got it. Okay, so there's minus and
Let me
cosh
let me
x.
look it up. 1 second.
Yeah, because it's not that big of a deal.
Yeah, it's minus.
Okay, cool. So obviously, if you take the derivative, and this, I think this is positive and that's negative. Whoops. Okay, obviously, if you take the derivative of this, you're gonna get cosh. So d dx of sinh x equals cosh x, and that's about as far as you'll go. I don't know. Do you guys have specific problems you want to do with hyperbolic?
Yeah, I can give you one right now.
Okay. Real quick, I'm gonna go get water. I'll be back in 10 seconds.
Okay. Abhinav, you got any questions?
Can you be my partner for the partner quiz?
Actually, let me think about that.
I
Yeah,
know on
probably.
above didn't do jack shit, so I'm just gonna have to go rely on someone else. I've been doing
Alright.
apes since like I got home and took my dog for a walk.
Okay.
So it's been like a run.
By the way, you guys are on recording, so whatever you say, we'll upload it to YouTube.
You're
All
gonna
right.
have to
Doesn't matter.
bleep out Abhinav swearing.
It's too
Whoa.
late. I'm not gonna go in and cut this stuff out. So, anyways, let's keep moving.
All right.
What do we want to do? What's the question?
Oh yeah. It's a definite integral. The upper bound is 2, the lower bound is 0, and then it's cosh squared sinh dx. I mean, it's just like a basic
Cosh
problem.
squared sinh.
No.
Wait, what?
Cosh squared times sinh dx.
Okay,
It's
you
pretty
should
simple.
cos. You mean cos squared x times sinh x
Sorry.
dx?
Yeah. Yes.
Okay,
Yes. Yes.
cool. Because you can get problems where those aren't a variable, and then those just become
Mhm.
constants. So, anyways, all right. This is just u squared du. Do I need to go
Mhm.
further?
Nope. I mean,
Okay.
yeah, it makes sense. And then when we plug it in, like, does he want us to simplify super far or
I mean,
no?
yes. I mean, there's a few key things. So again, let me just write these off to the side real quick. Sinh x equals e to the x minus e to the negative x over 2. cosh x equals e to the x plus e to the negative x over 2. So if you have like sinh 0, that's equal to 1 minus 1 over 2, so that's 0. So that should be simplified. Sinh 1 is e minus e over 2, so that's also 0. Yeah. No, it's not. That's a lie. Because it would be e minus 1 over e 2, and that doesn't resolve simply. So now cosh 0, let me see, cosh 0 is going to equal 1. And I guess that's about it, but here's the thing. This is a valuable tool because if part of your integral, it might be easy to switch to this, or depending on what you get, if it's like sinh 1 minus cosh 1, if you just actually plugged it in, you could get something simpler without the hyperbolics, because you could get e minus 1 over e plus e plus 1 over e over 2, right? Or I'm just going to put a plus here. And then those cancel out, so you get 2e over 2, so that's e. That's much simpler. And you should be able to see that and simplify when necessary.
Okay. I think that was my
But
only question
yeah,
related to
but
this. Like,
if it's complicated and clearly it's not gonna be simpler if you put it in terms of e, then don't do it.
okay.
And you might only put parts of your expression in terms of e because other parts are going to be too complicated. Just use your best judgment. Okay, do we have any other questions on anything else other than like trig powers to, or trig functions to a certain power and taking the integral?
Did you do the last two problems on the print sub page where it's like?
Do I have access to have one of you
I
guys
think I
send
sent them in this chat. Did I not?
that? Okay, let me check.
I did. Yeah,
Okay.
number 13, I think. Or no, number 12. Number 12. 1 over x. The integral of 1 over x squared plus 6x plus 8 dx.
Okay, yeah. So 1 over x squared plus 6x plus 8 dx. Okay. First of all, first thing that comes to mind, I already know what the method is, but I'll walk you through if this was a test and this was the first thing, like how I would go about it. First thing, I would check, is this factorable? 2 and 4, that adds up to 6. Okay, so we can do x plus 2 times x plus 4. Do you guys learn partial fractions?
Not yet. Even though Chen taught it to us
mean,
a little bit.
He taught it to us, but like he didn't teach it to anyone else.
Was it to do a problem like this? Because there's a way to do this without partial fractions that...
Yes, but like that was just for me because I asked him about it later.
Okay,
But
well, I'll tell you how to do it with partial. Did he teach you how to do this without partial fractions?
Yes,
yeah.
kind of. He gave an explanation.
Okay,
But
you know what? I'll just go over
well,
both ways right now. That's fine. Okay, so this is what we have. Okay, cool. But this doesn't really help. What I would really like is if I had, because we know how fraction addition works, if we could just decompose this into this. We don't know what these are, but theoretically, if there should be some sort of fraction addition we would do here, that would get this. So how do we do that? Well, we can create a systems of equations from this. So if we add these together, back together, we'll get a x plus 4 plus b x plus 2 over, I just mounted the terms, put it all over 1 and did that. Okay. So I want to know if there's any way this can equal 1. Right? Okay, let me just expand this out first. Ax plus 4a plus bx plus 2b equals 1. That looks like one equation, but this is a valuable thing, and you'll do this a lot once you reach differential equations. This tells us a lot of things. One, these have to be the x, there is no x on this side, right? This is 1 plus 0x. So that means a And I'm just gonna rewrite this for a plus 2b. Right? These are equivalent statements. Does that make sense, or should I go slower? Okay, cool. These are equivalent statements. That means a plus b has to equal 0. At the same time, 4a plus 2b equals 1. And all of a sudden, we have a proper system of equations. So we could say b equals negative a. So 4a minus 2a equals 1. So you get 2a equals 1, a equals 1 half. Okay, and then b equals negative 1 half. So now we actually know what we can decompose this to, right? Okay, so now if a is equal to 1 half, we get 1 half. This becomes 1 half. Right? I'm like splitting it apart and factoring it out just because it's simple. It's if I need to go slower there, let me know. But because you might not always want to do this. Actually, yeah, you will. But just like if you were doing this on a test and you wanted to make sure you got it right, please write down every step. But for now, minus 1 half. Okay. Does it make sense how I got to here now? Is everyone good there, or should I explain that more? I'll keep moving. So then this becomes 1 half ln x plus 2 minus 1 half ln x plus 4. And that's equal to 1 half ln x plus 2 over x plus 4. If you really wanted to put the 1 half inside, you could, but I think this looks nicer. Then plus c. Okay, that's method 1 with partial fraction decomposition. Does that make sense, or should I explain? Is there any questions on that?
When you are splitting the fraction, I kind of missed the part, like the second step off to the far right, the
Uh-huh.
a plus b parentheses and then times x.
Yeah, because
Why are you setting, first of all, why did you add a 0x? And then why did you set it equals to 0? Am I missing
okay,
something?
okay. So when I added these two fractions together, I got this, right?
Mm-hmm.
I'm trying to see if these, hold on, I'm trying to see if this can be equal to this. Does that make sense? The denominators look alike. The only thing different is that this is 1
Yeah,
and
yeah.
this is
It
that.
equals 1. Yeah, yeah. I
Okay,
understand that part.
so, okay, and then I added 0x to show that, okay, yes, we have ax and bx, right?
Mm-hmm.
We have ax and bx, okay, but on this side it's 0x. So that means if we go here, right, I just factored it out and put it off to the side,
Oh,
a
yeah,
plus b
yeah. Okay,
has
okay.
to
I
equal
see, I
0.
see.
And now 4a plus 2b has to equal 1. So from this, it gave us enough information to make a systems of equations.
Yeah, yeah. Okay, I see, I see. That was the only
Okay.
part that wasn't clear, but everything else makes sense.
Okay. Are we good? Is there any other questions? Or I'll show you the second way that you're actually supposed to do this since you don't know partial fractions yet, technically. And there's actually more stuff with partial fractions, so this is not all of it. I'm not going to go over the rest, but if you have like x plus 2 squared, x plus 4, then you actually have to do a x plus 2 plus b x plus 2 squared plus c x plus 4. Because if you mount your terms, both of these can contribute. Does that make sense?
Mm-hmm.
But
Yeah.
I'm not going to go over that since you guys will go over
I
that
have.
soon.
So when we were going over this with Chen during fourth period,
Yeah.
um, I took a picture of a partial fractions worksheet that he had. I think he was just working them out before we do the next unit. Do you want me to send that?
Sure. If you want to send it in the Discord for everyone to look at, for
Mhm.
now. Or you might want to wait until they actually get to the thing so that people aren't confused why it's sent now or they forget
Okay.
it. But that's fine. That works. Either way works. So what was the question again? I'll do it the way you're supposed to right now. It's
Yeah,
1
it
over.
was x squared plus 6x plus 8.
Okay. So let's say I tried factoring the bottom and it didn't really work out right. This is suspiciously close to a triangle problem. There's an x squared here, stuff going on. But for a triangle problem, I need two terms so that I could do a squared plus b squared, right? There's too many terms here. However, if there's too many terms here, what if I could remember back when you did quadratics and you were able to put it in vertex form?
Yeah, completing the square, right?
Yeah, so that's all we have to do here is complete the square, and that way we can have it two squared terms. So, how do you complete the square again? I think, all right, it's this middle, you divide that by
Yeah,
2,
b over
and
2
then you square it.
squared.
So we need a 9 here, but we only have an 8. So you lie and compensate. You put a 9 here, and then you subtract 1. Okay.
Mhm.
So then that becomes 1 over x plus 3 squared minus 1 dx, and then that becomes a triangle problem. Theta, let's make this x plus 3. Let's make this 1. This is square root x plus 3 squared minus 1. Okay, so cotangent theta equals cotangent squared theta is equal to 1 over x plus 3 squared minus 1. So that's one component. I'll box that. Second component, we need a dx. So we can get that easily if we just have this, and that is equal to cosecant theta. So negative cosecant theta cotangent theta equals dx. Okay, d theta here is equal to dx. Okay, let me zoom out because I can already tell this is going to be some work. Okay, so this integral is equal to cotangent squared theta times negative cosecant theta cotangent theta d theta. And this we were going to do trig functions to various powers. This is kind of adjacent to that. So let's solve that. This is negative cosecant theta cotangent cube theta d theta. Okay. What do we do here? Just say that this is equal to if sine squared x plus cosine squared x equals 1. We could say 1 plus cotangent squared theta equals cosecant squared theta.
Mhm.
And then you get tangent squared theta equals secant squared theta, or yes, theta minus 1. Okay, would that help to do here? Yes, I think it will. So it's worth a try. So I'm just going to put the negative off to the side right now. This is equal to, put over here, is equal to the integral of cosecant theta times. The other thing I was thinking is maybe we could do this by parts, but if we do that, we're going to get this would become b is equal to cosecant theta, and then du equals, that would just flip it so you get cotangent cosecant cubed, and that doesn't help a whole lot. Maybe it does, maybe it doesn't, but this is probably going to be simpler. So anyways, this is cosecant squared theta minus 1. Okay, let me distribute this inside. So this is cosecant cubed theta minus cosecant theta. And I'm just going to distribute this too while we're at it and split up the integral to save some room. So this is the integral of cosecant cubed theta cotangent theta d theta minus the integral of cosecant theta cotangent theta d theta. And this is easy because we can move this on the inside and we get cosecant theta. So that's one part. We have to do this still. I say that, let's see, if the derivative of cosecant is negative cosecant cotangent. Oh, okay, so this is just u sub cosecant squared theta times cosecant theta cotangent theta d theta. I need a negative here, so I'm going to put a negative on the outside, and this is negative u squared du. Does it make sense how I got from here to here?
Mhm.
Okay. Now, the question is, could I have actually done that earlier? I don't think so, because there's a power on the cotangent. Okay, so this was the right track. So this is u cubed over 3. So the final thing is, or it's negative u cubed over 3. So it's negative cosecant theta cubed theta over 3 plus cosecant theta. And then we have to go back to our triangle here. Cosecant theta is x plus 3. So it's negative x plus 3 cubed over 3 plus x plus 3. And if you wanted, and then you have a plus c, but if you really want it to be fancy, you can absorb the plus c in the 3, so it's just negative x plus 3 over 3 plus x plus c. Okay. Are we good there? That's the second method.
Yeah.
But that got us a different answer, so I'm a little bit confused. The ln.
Yeah.
Okay,
Not. I mean,
let me see which one is the right answer first.
now I go. Sorry.
X squared plus 6x plus 8 comma x. Okay, the ln answer is the correct one. So my question is, where did we go wrong here?
Was it
Actually,
maybe?
there's
I mean, it could
no.
be during the by parts, right?
Wait. There's definitely because with the cosecant we should have gone ln stuff. So there's definitely something going on here. Let's
There's
see.
something with the by parts.
Uh, there was no by parts. Was there?
Did you not literally? Oh, you didn't do by parts at all.
Okay,
No, you
let's see.
just split
Okay,
it.
first of all, also there is a negative here that I forgot to incorporate, so that's part of it. But let's
Oh,
see.
wait, hold on.
Cosecant, cotangent cube theta d theta. Okay, then you got cosecant theta, cosecant cube theta, cotangent theta. Minus secant cotangent d theta. Okay, let me see if I did this integral right first as well. Cotangent. Cotangent x cubed times cosecant x. So it's telling me it's the calculator. It's highly it's a different form, but it's sine squared x minus 1 over, which is what we got. So the only thing I can think of, the only thing I can think of is that this must be wrong. So let's see. We have 1 over x cubed minus 1 squared cotangent theta. So that goes to that. And then you have minus 1. Yeah. And then you have your dx. and you multiply these. You get that. So what is going on here? Cotangent theta. It is that. No, it's not. No, it's not. There it is. Right there. It should be tangent theta. This tangent theta is equal to 1 over square root of x plus 3 squared minus 1. Okay, cool. So that's where we got our issue. And so, like, when people say you can't check your answer in calc, technically, there are, with integrals, there's oftentimes a few ways you could do it, and you can make sure you get the same answer. But anyways, okay, tangent theta, so then you square root that, so it's tangent squared theta. Okay, so now, the integral is negative tangent squared theta times, or I pulled the negative out from this, so it's cosecant theta cotangent theta d theta. Okay, so that cancels out. You get 1 tangent theta. So you get tangent. I'm just going to put this in terms of sine and cosine because I can tell there's only going to be one thing in the numerator, or maybe nothing in the numerator. So now, there we go. Now we have an ln because this becomes 1 over cosine. So this is secant theta d theta. So it's ln secant theta plus tangent theta, which is ln secant theta here is cosine. So it's x plus 3 plus 1. So it's x plus 4 over square root. And I'm sure they are equivalent, but we can actually do that too. If you want to actually make sure they're equivalent, like on a test, you definitely would want to do that. You would say this is the square root of x plus 4 squared. Is that the best way to do this? Let's see. We might as well try. So then that's 1/2 ln plus 4 over x plus 3 squared minus 1. Are you guys following, or are you guys getting lost? What I'm doing here?
I'm following it, don't worry.
Because in the other thing, we got minus 1/2 ln x plus 4 over x plus 2. And if the whole point is of you doing it multiple times is check your answer, you want to get the same thing. So x plus 4 squared. So in your ln, you get x squared plus 8x 16 over x squared plus, I don't think this is going to work out. Wait, let's see. X squared plus 6x plus 8. That's definitely not going to help. Interesting.
Do you need to check it like this? I feel like it makes sense.
What did you say?
Do we need to check it like this?
I
feel like
mean,
what-
yeah, you do want to make sure these answers are equivalent. So secant theta, tangent theta is 1 over square root. Yes, secant theta is x plus 3 over, so it's x plus 4 on the top. And then, so it's telling me that negative 1/2 ln x plus 4 over x plus 2 is equal to ln x plus 4 over square root x plus 3 squared minus 1. I guess if you yeah, wait. So if you do x plus 2, x plus 4, if I move the negative inside, and then I do, yeah, I don't know. These should be equivalent. I did something wrong again, but I don't think I did. Let me plug this. Let me just like subtract these two and make sure they're equivalent. And then I'll post later if I can how they are. Okay. I'm not sure. I'm not sure. Oh, what if Okay, yeah. I don't know. These should be equivalent. I think I'm messing up somewhere here. Tangent, cosecant, cotangent, sine, cosine, secant, ln, secant theta, tangent theta. Yeah, it's close, but there's something mismatched here. I'll check it out later because I want to get to raising the power stuff, and then I'll
Yeah.
post it.
That was when he showed us in class. It was pretty lengthy. I didn't write all of it down. Yeah,
For
on our sheet
what?
there's the like trig functions to higher powers. So like
Okay, we can.
tangent to the
What I want to
he
do
has
is I want to go through every single trig function up to you said fourth power or fifth?
so he said the highest he'll go on a test is the fourth power. I really want to see the sine to the fourth power.
Okay. We'll do this one by one because I can do them quickly, I think. Um,
Mhm.
First one, sine theta, and I'll go with that is negative cosine theta. Okay, cool. Sine squared. If you use cosine 2 theta for that equals sine squared theta. So you get equals 1 minus cosine 2 theta. So you get sine equals 1 minus cosine 2 theta over 2. And then from there, you guys know what to do, right?
Mhm.
Yes? Okay. Okay, sine cube theta. So we know that sine theta, or sine squared theta equals 1 minus cosine squared theta. So sine theta, 1 minus cosine squared theta, d theta. Okay, so you get sine theta minus this is pretty simple from here. Do I need to go any further?
Yeah, those are fine. I got that.
Okay, cool. So now let's do sine to the fourth theta. Okay. So we know that sine squared theta equals 1 minus cosine squared theta, so that's a good place to start. So we get sine squared theta d theta, which we know how to do from earlier. I'm not going too fast, right? Sine squared theta cosine squared theta d theta. For now, are we in the right spot?
Wait, yeah. Uh-huh.
Oh
What do you
wait,
think?
why did you like separate the cosine squared theta? Is that like? Oh wait, never mind. I'm done.
No, you
I
just
just
Yeah,
distributed
I get
I
the
it.
just did
I
this,
get it.
distributed it, and split the
Yeah.
integral.
Okay.
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 Now again, what Shao always says, what do I want? How do I get there? This looks really suspiciously like you have a sine theta and a cosine theta. It'd be really nice if I didn't have any powers, and I know that sine 2 theta is equal to 2 sine theta cosine theta.
wait, pause. Isn't this literally just sine squared? Wait, oh, it's a theta. Never mind. Never mind.
Okay, so I want to get as close to this as I can. So I've moved the square to the outside. These are equivalent, right? Now I put a 2 here. Okay, I'm closer, but I have to compensate. So I put a 1/4 out here. Okay, so now this is 1/4 sine 2 theta squared. And then is this doable or should I continue? Because it's the same as this, just with USA. Okay. Did that make sense how I got through my thought process to get to here?
Yeah,
Or
that makes sense.
okay. It's always what do I want and how do I get there? Okay. Let's do cosine theta. Cosine theta d theta. We know that. Okay. Cosine squared theta. We use a half angle. Do I need to go over that or are we good?
Oh, no, the half angle thing is fine. I know how to do that.
Okay. Cosine cubed theta. You know that cosine squared theta equals 1 minus sine squared theta. So cosine theta, 1 minus sine squared theta d theta. Okay, cool. So you get cosine theta minus cosine theta sine squared theta d theta. Okay. This is u sub and this is easy. Do I need to continue or can I go to cosine to the fourth?
You can continue, but
Okay,
I'm just looking
then
at
let's
the
do
way
that.
that wait. I'm just looking at the way that Ken showed us how to do the sine to the fourth, and he had us like doing weird like separation and quadratics, where he did sine squared squared, and then he did the identity for like half angle, and then squared that, and then jumped from
Okay,
there.
I mean we can do
We
that
got
too. So sine squared theta squared d theta, right? And then you use your
yeah.
half angle to make that yeah, that's not too bad. And then you get okay, we'll just do it that way.
Mhm.
But the way Shao taught us, and I think the way that's more emblematic of you using your concepts is the other way. But anyways, this works too. And honestly, this is pretty neat. So 2 sine squared theta equals 1 minus cosine 2 theta. Sine squared theta equals 1 minus cosine 2 theta over 2. Okay, put that in there. You're going to get a bunch of cosine squared 2 thetas, and then you break it down even further. I'm not going to do that because that's super long. Unless, do I need to?
Not really.
Okay, and so you're telling me that, so for sine to the fourth, I guess I'll just post it since I guess Chen didn't know the other way to do it. Um, just, let me write that down. I'll post that in the Discord.
Mhm.
Okay. Or I might just give timestamps. That might be easier. Okay. Anyways. Um. Okay. So we did sine and cosine. What do we want to do next? Secant?
There's tangent and there's secant, but they seem
Okay,
like they're
let's
gonna
do
be
tangent. Tangent theta, d theta. We know how to do that. Sine theta over cosine theta, d theta. And then u sub. We're good there, right?
Mhm.
Okay. Tangent squared theta, d theta. Um. So you know that tangent squared theta
Isn't it
plus
just
1.
oh, I was gonna say sine squared. Never mind.
Because if you do sine squared theta over cosine squared theta, and then you convert these to half angles, you're going to get a fraction of half angles over a fraction of other half angles, which might not be super neat.
I mean, won't it just simplify because they're both over 2?
Yeah, but then you'll have like you'll have 1 minus cosine 2 theta or something like that. Maybe that'll work. Actually, we might as well try that. Okay, so, oops.
Oh, wait, no. I have this written down. I just used the secant, like secant squared minus 1.
Yeah, that's what you're supposed to do. But also, I kind of want to do it this way now that
Half
you
angle.
said it.
Okay.
Cosine squared theta d theta. Okay, sine. What am I doing? Oh, so sine squared theta equals 1 minus cosine 2 theta over 2. Cosine squared theta is equal to 1 plus. Yeah, cosine 2 theta over 2. So you get you'll get 1 minus cosine 2 theta over 1 plus cosine 2 theta d theta. Okay, and then what I'm thinking is we multiply by the conjugate, you'll get 1 minus cosine 2 theta. You'll get, if you do the conjugate, you'll get 1 minus cosine squared 2 theta over 1. Sorry, no, you're right. The over here 1 minus cosine 2 theta. This is squared up top, and then this is 1 minus. Okay, and then that becomes on the bottom. Okay, actually there might be a path out of this. So because then that becomes sine squared 2 theta, and then you expand this out, so you get 1 minus 2 cosine 2 theta plus cosine squared 2 theta. Oh, wait. So then, no, because even if you set that equal to tangent, because you're just gonna get this again over here, even if you broke it apart, and that's tangent squared, and it's positive, so it's just gonna cancel, and then
Well, won't you get wait. But if you have tangent squared on one side and then you
but there's a positive, so you would subtract it from both
okay,
sides,
never.
and then I actually don't know what's going on here, unless I did the only explanation, maybe I did something wrong along the way. Let's see.
Mhm.
So that goes there. You do that.
Is there another way to do it? Like, would this work out? Should it?
Yeah,
Because
this
my
comes out to 0, so this just decomposes back. Like with parts, when everything cancels out, you get 0 equals 0.
mhm.
So
Yeah.
when you take the integral of both of these, it'll come back to 0.
Mhm.
So
You could just use the
yeah,
secant squared minus 1 at the
yeah,
end.
that's it. That's the way you're supposed to do it. I was just curious if this worked. I don't think it does. Maybe it does. Maybe it doesn't. Maybe I didn't do it right, but that's fine because that's not the best way to do it, anyways. Okay, tangent cube theta. Tangent squared theta equals 1. No, tangent squared theta plus 1 equals secant squared theta. Okay, so then you'll do tangent theta times secant squared theta minus 1 d theta. So we get tangent theta secant squared theta minus tangent theta d theta. There's a d theta here. We know how to do this, right? So that gets swept away. I'm just showing the parts that are new because you guys know how to do that. Okay. So this is secant theta times tangent theta secant theta d theta. That's a u du, right? U du. So then that's secant squared theta over 2 plus that. Okay, are we good there?
Yeah.
Okay,
And then
do
now
tangent.
tangent to the
Tangent
fourth.
to the fourth.
So I remember
Okay.
him telling us for this one, we're gonna use like Pythagorean identity, but plug it in at different times. It's not just like willy-nilly.
I mean, I'll try and remember how to do it. So tangent equals 1 minus, or sorry, secant squared theta minus 1.
Mhm.
So you go there. You get okay, this gets swept away, right? We know how to do that already. So, how do we do this? This is, let's see.
I mean, isn't it just u squared du? U equals tangent.
Yeah, it is. Okay. Yeah, it is. So then, there we go. Pretty simple. Okay. Cool. Okay. So then the next thing is
You want to do more than these, or ask a question?
yeah, you can ask a question and then we'll keep going because we have cotangent and then secant, cosecant. What's your question?
Okay. My question is, let me find it first. Did we do number 13 on the trig stuff? Should be in this.
Yeah, we did last time.
Okay, then we can leave that alone.
But how did we do it last time? I think we
Okay.
I think it was just trig sub, and then once you got to the trigonometric identity, there was a thing. It's in the last video.
Okay.
Do you want to go over it again, or I will?
It's
I
okay,
will.
it's okay. I found one that was also kind of like, I didn't want to do it just yet. It's a definite integral. The bounds, upper bound is 1, lower bound is 1 over root 3.
Okay. And what's the integral?
Then it's x times inverse tangent of x dx.
Okay. So we can just u dv u equals x du equals dx dv equals tangent inverse x dx. So now we're gonna have to put this off to the side. V equals the integral of this, right?
Yeah.
The integral of that is, we did that
We
earlier.
should do another by parts, right?
Yeah, we'll just do it again by parts. Tangent inverse x dx. This is dv. This is u. U equals tangent inverse x. So du equals 1 over 1 plus x squared. dv equals dx. V equals x. So this is equal to x tangent inverse x minus v du. Okay, put a 2 here. 1/2 to compensate, so this is 1 over u du. So this is ln 1 plus x squared.
Yeah.
Half. Okay. All right. So
I think
I'm
that
going
was the
to
only other question I
wait.
had.
Wait. It's not done yet, but because that was just our v.
Yeah.
So v is equal to x tangent inverse x minus 1/2 ln x squared. Okay. Oh, but then if you do v du, huh? Actually, no. This is possible. Yeah. Yeah, it's possible. Okay. U v. Okay. So this is equal to. Let me just. I'm not gonna compute the definite part. I'm just gonna actually do the integral.
Mhm.
Yeah. Okay, x tangent inverse x is equal to uv.
Wait, does that say x squared?
Is that x squared up here?
No, it's just x.
No, here it's x squared because it's this times this.
Yeah.
Okay, minus x over 2 ln 1 plus x squared. Okay, uv minus, now here's the real hard part, v du. Well, first of all, this can be moved over to the other side, but then what about the other part, which is this 1/2 ln 1 plus x squared dx. Okay, first of all, this can be moved to the other side, so this really becomes a integral of 2 tangent inverse x dx equals all this dot 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 plus 1/2 integral of ln 1 plus x squared dx. Okay,
And then do we
this
simplify
has to be done
further
by
from
parts.
there? Okay. Yeah.
Okay. Yeah, and then hopefully this doesn't unravel our logic, but it's worth a try because we're picking a different kind of u and v. We'll see if it actually does that. So du equals 1 plus, this becomes 2x over 1 plus x squared. This looks eerily similar to stuff over here, so I'm worried it might undo our logic, but we'll see. dv equals dx, x, v equals x, so it's minus
That's
x.
exactly what we had earlier.
Yeah, okay, so this does undo our logic. Okay, let's see. Let's see. ln Huh. This is difficult. How could you do this? Okay, I think maybe it might be easier to flip the u and the v here, which is a little interesting, but it might work. X tangent inverse x dx. Make this our u, make this our dv. I'm worried it'll introduce complexity, but I think as long as you can remove the tangent inverse x, I think you can deal with increased powers of x for a little bit. So u equals tangent inverse x, du equals 1 over 1 plus x squared, dv equals x dx, v equals x squared over 2. And then there's a plus c here, but I talked about how last time those cancel out always. That initial plus c over here. Anyways, uv, so this whole thing is equal to x squared over 2 tangent inverse x, uv minus v du, which is
I would put the 1/2 on the outside. Do we need
1/2,
to be?
yeah. 1/2, and then x squared over 1 plus x squared dx. Okay. Question is, how do you do that?
Could this be a trig sub problem or no?
Yeah. I'm thinking maybe, let's see. 1x square root 1 plus x squared theta. So you get cosine is 1 over this, right?
So it's tangent squared and then
Cosine theta, hold on. Let's make sure we're doing it correctly. So cosine squared theta is equal to 1 over 1 plus x squared. Box that. Okay. And then tangent theta is equal to x. So secant squared theta d theta equals dx. Okay? So you get,
well, wait.
so you
Don't you
get d theta.
want pause? Oh, okay, yeah.
Oh, wait.
It's
Oh, we don't have the x squared on
wait,
the top. We don't have the x squared on the top.
it's
I
just
forgot.
tangent squared, right?
Yeah, so tangent squared. And then so you get tangent squared theta d theta. And we know how to integrate that, right? And then you can go from there.
Mm. Yeah.
Because it's this times this times this. So it's
Yes,
cosine squared times secant squared times tangent squared theta times d theta. So then these cancel out, so you're left with tangent squared theta d theta. And then we know how to do that, right?
Mhm.
Okay. So that's how you do that question. So the key here is realizing, okay, yeah, usually with our inverse trigs, we make this usually with parts we make this our u because it degrades, but the issue is means we keep our tangent inverse, and that's really annoying. So instead, the lesser of two evils is that we remove the tangent inverse and we just deal with this. That's kind of that's the logic you're supposed to go with. Okay.
Right. I think that was the only other question I had.
Okay, so where were we? Did we do cotangent?
I feel like the
Yeah, we did cotangent.
And we did tangent. Up to the fourth.
We did tangent 2.
So then it's
I
just
don't think.
secant.
Yeah, we did up to the fourth. Yeah.
Okay, so just secant. Okay, secant theta d theta. We know how to do that. Multiply by the top and bottom. Get the ln, like Chen showed you in class. Are we good there?
Yes.
Okay. Secant squared theta d theta. That's pretty obvious.
Mm-hmm.
Okay. Secant cube theta.
Secant.
So tangent squared theta plus 1 equals secant squared theta. So this is tangent squared theta plus 1 times secant theta d theta. So this is secant theta tangent squared theta plus secant theta d theta. D theta over here. Two integrals. That secant we know how to do, so that's swept aside. So now this here, how do we do this? We could say tangent theta is our u, secant theta tangent theta d theta is our dv. I don't think there's a better way to do this. One isn't coming to the top of my head. So we get u equals tangent theta du equals secant squared theta dv. Oh yes, this is how you do it. And then dv equals secant theta tangent theta d theta. V equals secant theta. So you get, now, here's an important thing to notice. You're going to get v du. So you're going to get the integral of secant cube theta. That sucks. However, we can just do the thing where we set it all equivalent to this. So the integral of secant cube theta d theta equals, it equals uv tangent theta secant theta minus secant cube theta d theta plus the integral of secant theta d theta, which we just put off to the side. And then you move that, and then you do it over 2. So we're good there?
Yeah.
Okay. Um, okay, so secant to the 4th theta. Secant to the 4th theta. Okay, let's try this out. So tangent squared theta plus 1 equals secant squared theta. So this is equal to secant squared theta, tangent squared theta, plus secant squared theta, d theta. I'm not mistaken there. I used one of them, and then I had a secant squared, and I distribute and split out the integral. So we're good there. Okay, that goes away because we know how to do that already. This we've done earlier. It's just u squared du. So we're good there. Okay, is there any questions on anything I've done so far? Because I'm on the last. We'll do cosecant.
No question.
Okay, so cosecant. We know how to do cosecant theta d theta. It's similar to secant. You multiply by the top and bottom, you get ln cosecant theta minus cotangent theta. Are we good there?
Mm-hmm.
Okay. So now it's cosecant squared theta d theta. We know how to do that. Put a negative here. It becomes negative cotangent theta plus c. We're good there?
Yep.
Cosecant cube theta d theta. Okay. Cotangent theta squared theta plus 1 equals cosecant squared theta. If I'm not mistaken, that's correct. So, you put that in, you get cotangent squared theta cosecant theta plus cosecant theta d theta, which we know how to do. That goes away. This here we do by parts. Do you want me to do the rest of this? But because it's exactly like secant, where you do it by parts and then you add it over.
Sense. It makes sense.
Okay,
I mean,
and then
will it change when we do it to the 4th, or will it just be like secant?
it'll probably be the same. Because I mean, if you want to know why they're the same, isn't it cosecant 90 minus or pi over 2 minus theta equals secant theta or something like that, right? So
I know what you mean.
it's the same thing. It's just shifted over. So the integrals are gonna have the same thing. Anyways, that's like a more, if you wanted like, I guess, a slightly more rigorous reason for why. But anyways, cosecant to the fourth theta d theta. So then that's equal to that makes no sense. Hold on. What is it? Cosecant squared theta equals cotangent squared theta plus 1. Okay. So you get cosecant squared theta cotangent squared theta plus cosecant squared theta d theta over here. Okay. And I'm doing a bunch of shortcuts here. You should be writing it out on the test. Is that clear? Okay, cool. Okay. Cosecant squared, cotangent squared. And then from here, you could just say u squared du and put a negative here, a negative on the outside. Are we good?
That makes
Is there any questions on anything I've done so far? We technically have 20 minutes until I gotta go. So, any other questions?
I don't think so.
Okay, so the one thing I wanted to do was cover. I'll post. What was the one that he did differently? It was sine to the fourth theta.
Mhm.
Okay, I'll post that, and then if I can figure out why when we did it by parts or by completing the square, why we got a different answer, I'll post that too. Is there any other questions? Anything at all?
None for me either. Not right now, at least.
Okay, if you have
Probably
any
going to
other
be a lot
questions,
after the quiz.
got it. If you have any other questions between now and I guess the day of the quiz, just send them. I'll try and answer them. Yeah,
Okay.
thank you for coming. That's all for today, I guess.
All right.